first, let's just throw something out there. This is an integer programming approach to the same problem of learning constraints, and it outperforms StatNet on Sudoku. But this is an integer programming, solution. So, that's a nice result, great for that community. But if you care about, doing something in an end-to-end fashion using a neural system, this is clearly not doing. Now, of course, if you're of an engineering mindset, you could always think of, hey, why not just have a separately trained CNN on the front end that produces results and sends it to that. Hey, of course you can do that, but I think there's some good arguments for wanting to do stuff in an end-to-end fashion because the general idea there is you're going to get, less error. But that's the key question, okay? If those visual Sudoku results go away, then, maybe you should just do something like that instead. It's getting a better answer. Okay, so a year after StatNet, Chang et al. Reviewed it, and these were kind of the big things that they bring up. Label leakage, initialization, hyperparameters, and training decisions, and then the whole symbol grounding / transduction issue. So the original paper claimed it was trained in an end-to-end fashion. And like I said, however, while the samples were visual, the output was purely symbolic. And here's what we mean by that. You have, the zeros would be the numbers that need to be filled in for this square. But then you're feeding ground truth that has those numbers with, or typed in with numbers. So they said, hey, that's kind of cheap. That's their point. Because, you're essentially supervising it with additional data. So, okay, well, let's put the label leakage aside, and they said, let's just run it and just see if we can reproduce the results. And this is where the weight initialization issue comes up. And they claim in their work that around 80% of the time, it totally fails. And so the results go from like 99% to something like 18%. And what they did, that was kind of interesting, they looked at what happened with the convolutional layers, learning the digits. At the same time, they looked at the overall performance on solving the puzzle. And here on this side, you see an example of a run that went well. So here's the performance on learning the digits. Notice the overall performance is 0 until it gets to a certain point, certain ability for learning the digits. And then it has sort of this logarithmic improvements in the handwriting recognition task and this huge improvement in the overall task, right? Well, what if it gets unlucky in the weight initialization and it takes a while to learn the digits? Now notice for handwriting recognition, this is probably still not a horrible run, but it's taking much longer to converge to something useful. And because of that, this guy up here never can really get to work. And so that's where you get total failure. Yes?
Would that imply then that it would be better to just have a pre-train the network until convergence and then see to do the coordinate descent with the solver?
Yeah, that's I think a fair point. I will get a little later in the third paper though that comes up with a different solution to that. So I think that the reason that they didn't want to just do pre-training is that would still be considered cheating because you have to have the labels of the handwritten images to begin with. Yeah.
I had a doubt. Why is this happening? So, if supposing we directly feed it the labels without the visual recognition, would it work always then?
So, well, it might, I think it probably would. If you would just feed it and train the CNN by itself and treat it as an entirely separate system, I think in this case, it probably would. Yeah, but that's not what they're trying to demonstrate in either this paper or the previous one.
Yeah, I still quite don't understand why there's like, after like the MIDs have recognized the digit, but on the upper hand of the right hand side, the visual Sudoku didn't show up any result. Why is that?
Well, because it just never had anything to work with.
Why? But they already recognized the digit, right? Between like 60 and 40 months. Like between the left hand side of the graph and the right hand side of the graph, this did not explain.
So the this is still improving though.
Yeah.
Albeit at a slower rate. And so I think that is probably has something to do with it, where this is leveling out at that 85%. Now, whether or not if you did another bunch of epochs, this would maybe slowly increase, although I would suspect that maybe this hit like kind of some local minimum, and it just never escaped. That's sort of what I think.
Sort of like what he was saying. I mean, once you have the image recognition kind of getting results, why is it that after that we wouldn't see any impact on the visual Sudoku results?
Well, again, because I think what happened here is it leveled off. Because I think what's going on with this one is it's wandering around the search space and getting stuck in the valley. Where this is, keeps on going, you still have this improvement.
Well, is it to say that nothing from this is getting fed into the visual, into the?
Well, it's feeding garbage into it.
Oh.
Because I think you need to have, because this is a combinatorial problem. So you need to get to the point. So, so when I was in grad school, there was an old joke that said that like you can always get to like 85% accuracy. Okay. You could always get there for any, that's kind of like the joke, right? And so, getting to these higher levels of accuracy is more difficult. And if you remember from the earlier discussion, we got on like maybe like the first or second lesson, there's a theorem from statistics that says something like you need, K improvements, you're going to have like K to the fourth more parameters or something like this, right? This is kind of what you're getting here, because you need to have extremely high accuracy to actually begin solving the problem in the first place. And so it's getting, out of that valley is, I think, tough. Where when you look at the handwritten digit recognition problem, that could still be, you can still argue that that's not bad performance. Yeah.
So, like when we were talking about the problem of label leakage, so they were saying that they're converting the image to sort of a matrix, let's say, and we're feeding the matrix into this SciNet. So that is the problem that they're talking about.
So what happens is the input is partially filled in matrix with digits, handwritten stuff, and the output is symbolic digits for the whole matrix, including the stuff that was the input. So they argue that, I haven't even talked about that. This is even disregarding label leakage. This is still with the label leakage, everyone. Okay, that's what we're seeing here. So their first argument is even the good results were way worse than as brief. So it goes to like 13% or something. But it only goes that because they say for the weight initialization, it's about a fifth of the time it works. Yeah.
Is it also possible that the result could be because by the time MNIST learned the digits, it was too late for the network to catch up?
I mean, yeah, it could be, but you see, I think the problem with that argument is you could expect to solve that problem by just adding more epochs. And I mean, this is not the greatest chart to read, but if that is increasing, it's very low. It's increasing extremely slow, and likely with noise, it's flattened out because it reached a local optimum. That just be my guess. I didn't do the experiment. They didn't have that detail. All right, let's move on. Yeah, so here. Okay, so a little bit of background. So transduction is the problem of if symbols exist, how are perceptual states mapped to symbols, all right? So, we talk about like explainability a lot in this class, right? So who can explain why that wall is purple? Or who can explain that wall being purple? You can't. You just look at it and you know it's purple because you learned that like when you were a toddler. And so the color purple is grounded. The neurons that detect purple in your eyes know that, associate that with the symbol in your brain for the color purple. And so that translation from the neurons to a higher level symbol in your head, the cognitive scientists call that transduction. And then symbol grounding is the other way. It's, I have, the color purple, what does that map to in terms of neurons? And so the authors of the rebuttal SatNet paper said that they didn't do a good job solving the symbol grounding problem. It's technically transduction by what the cognitive scientists call it. But they're complements of each other, just to go in different directions. So this is an example of failure in symbol grounding, where the car is identified as a cake. So you look back, we look back at the neurons from the cognate that came up with the idea that that was a cake. And then we look at it as a person and we say, well, that's obviously a car, because it has like one of these papers where they have a funny paint job to throw off the network. Now, the problem with SatNet isn't that. It was the other way around. It wasn't transducing the neural stuff into proper symbols. And so just, you can check that out in the deck. Oh, another question. But anyway, I mean, going from physical objects, neural activation to perceptual states, transduction turning it into symbols, and then going and reasoning about it. So this is not from AI or CS, it's from the cognitive science. Okay, so, well, the thing to do then is, well, let's mask the portion of the output so that the algorithm is never exposed to the input data. And then when they mask the output on the visual case, results for both training and testing go to 0, according to the rebuttal paper. And then here we see the training and testing numbers drop by about 80% of what they were from the original paper based on weight initialization. The rebuttal paper did show, though, if you just mask in the original case, which really doesn't make any difference because it sees the first part of the puzzle in the input, they're getting pretty much the same results as the original paper.